Why is there 3 separate trash cans?
Here is our first question. And we'll kind of go over this together-ish. But at some points in time, I'll say, now do this. So all last week we were doing pulley, or not pulley, we were just doing mass systems, where one mass is sliding one way, the other mass is sliding the other way. This week we're going to do pulley systems, where this week is today and tomorrow. So for the first one, and I was going to set this up, and then I honestly just kind of ran out of time this morning, but I think we can envision this in our mind, what's going to happen here. Here is the pulley right there, and we got a mass of M1 on the left-hand side, mass of M2 on the right-hand side. I'll turn the lights off so we can see. It says a 2 kilogram mass and a 0.5 kilogram mass are connected by a string. String is stretched over a pulley. Determine the acceleration and the tension in the string. First part says draw a free body diagram for each separate mass. You guys can do that, and I'll do it up here. Make sure that you make it qualitatively accurate, meaning that arrows that are the same length are the same length. Arrows that are bigger are bigger. Arrows that are smaller are smaller. FG, let's call that FG1 for the first one, just so I can kind of differentiate. We got the force of tension up. For mass 1, should the force of tension be bigger, smaller, or the same as the force of gravity? Well, which way do we think this thing's going to accelerate?
It's going to go down. So yeah, it's got to be smaller.
We think it's going to accelerate this way?
Yeah.
Yeah, I buy that. That's what's going to happen. So the force of gravity has to be bigger than the force of tension. So force of tension up. So that's for the first mass. What about the second mass?
Would the forces of tension be equal for the first one and the second one, the one that we're about to draw?
Yes, sir. Forces of tensions would be equal because of Newton's third law. So if I drew this force of tension that length, then the force of tension for mass 2 should be the same exact length as the one that I just drew.
The force of gravity should be smaller.
And the force of gravity should be smaller than the first force of gravity because it is smaller. How should that force of gravity compare to the force of tension that we just drew? Should be smaller. Because mass 2 is accelerating up. Yes, no, or meh so far?
Yes.
Cool.
Yes.
Yeah.
Next one. Draw a free body diagram or draw an FBD for the system of 2 masses. Okay. Ready? Pretend that you take this and you stretch it out like this. Ready?
With the pulley still there.
So I'm going to try and draw it. I don't have yellow markers, so we'll make that one green.
You think they give us primary colors?
I know. It's messed up. So there we go. I took that and I stretched that out. Now, let's say we take these 2 free body diagrams and turn them. And the only reason we're doing this is just to help us understand what's going on a little bit better. So if we looked at the system of these 2 masses, like that, the free body diagram on our blue mass, we just drew it up here, right? But then if we're going to take this and we're going to pivot it, force of tension that way, a bigger force of gravity that way. And I know that force of gravity is still acting down and force of tension is still acting up. I'm just kind of taking it and pivoting it because it'll just help us kind of understand what's going on a little bit better once we get to the next step. And for the green mass, this force of gravity should be, I'm sorry, this force of tension should be which way? Left?
Yeah.
Wait, are we pivoting the same way?
So we took it and we just kind of,
I thought it said to make it for one of them. Like you got to combine them and then just make one. Why are we making 2?
well, that is what we're doing. I'm just trying to show one other. We are trying to combine the 2 of them. There's just one intermediate step because it's pulleys. So then the force of gravity this way for the second one. Now, when we look at the system of the 2 masses, if I put in dotted lines our two free body diagrams like this. Do you guys agree that the Earth is not within the system of our two masses? So that means when we shrink our two masses down to a point, like this, what are our outside forces?
Force of gravity.
To the two force of gravities. One force of gravity, and it doesn't really matter which way we make them as long as they're opposing each other. It might make our brains understand it a little bit better if we're just thinking that one force of gravity is causing it to accelerate one way, and one force of gravity is fighting against it accelerating. So what I just did there is I took it and I pivoted it back, but really the only reason I did that intermediate step was to show you, hey, these forces of tension are equal to each other because of Newton's third law, and they are within our system, so they go away. Yes, sir, Mr. Logie.
So when we're making these on something that's graded, should we put definitely 1 and 2, or does it not matter? Like force of gravity 1, force.
The only reason I'm doing that is because we have two different blocks, and I just think it's easier to show this one is the force of gravity from the blue block, this one is the force of gravity from the mass 2 for the green block. Yes, ma'am?
But didn't you say that it was gonna, that mass one was gonna accelerate, like, that one was gonna accelerate down?
Mm-hmm.
So if the force of gravity is, wait. Yeah, if that's for the two of them, and the force of gravity one is greater, then doesn't that mean that the whole thing is going down in that?
So what we did is we kind of took down and made, and this is where it gets weird, where down isn't really down. We're looking at it that this whole thing just accelerates this way. So we took the fact that mass 2 accelerates up and mass 1 accelerates down, and we just said, okay, it's just going to accelerate along this line like that. And then just to help us kind of draw our diagram right here, I agree that, do you agree that force of gravity 1 is fighting against force of gravity 2 in order to make it accelerate? That's the only reason that we drew it like this. We could also draw it like that, and it would be the same thing. It's just one fighting against the other one to make it accelerate. Anything else?
Really, we're good. It's okay.
Somebody turn them off. And
Okay, so if we're going to move on, now that we drew our diagram, it says determine the acceleration of the boxes. Let's choose our system as system is both. Determine the acceleration. All right. This looks like a forces question, and to find acceleration, we'll use Newton's second law. A equals F net over the mass of the system. Really hope I didn't get that. That was awesome.
Mr. Jeff,
Yes.
real quick, you said you can't stay after today or tomorrow, right?
Right. Yeah. I have a meeting for, we have a meeting for Pulley today, and then on tomorrow I have a faculty meeting. What's our net force acting on our system of the two boxes?
FG1 minus FG2.
FG1 minus FG2. So A equals FG1 minus FG2. And what's the mass of our system?
2.5.
2.5 kilograms. I'm going to first do it in terms of variables, and I'm going to write it as M1 plus M2. Now, just for the sake of making our lives easier, let's do this. Right now, G equals 10 meters per second squared. Find me the acceleration of that system. Or actually, find it for yourself. Don't find it for me. You don't need to do things for me. Find it for yourself.
That's inspiration.
That's what I'm here for. answer that I got when I did this earlier was 6 meters per second squared, I believe.
I got 6.
I got 6.
Okay, so 6 meters per second squared is our acceleration. Now there's a little self-check we can do with this. What's the highest possible value that these things could accelerate at on the surface of the Earth? Like the highest possible value would be if M1 was just falling by itself without M2 fighting against it. And if M1 was just falling by itself without M2 fighting against it, it would accelerate at 9.8 meters per second squared. Or in other words, as we approximate it for this, 10 meters per second squared. What's the minimum possible value for the acceleration?
9.8 meters.
0, if it's just sitting still.
Oh.
If M1 is samesies with M2, does it accelerate at all? No. And then let's think if M1 is 800 kajillion kilograms and M2 is 0.000000001 kilograms. How fast does it accelerate at that point?
Really?
Very fast.
Pretty fast, but faster than 9.8 meters per second squared? No. So built in by the question, since these things are accelerated on the Earth, we have a self-check. If you get an answer, acceleration is 15 meters per second squared. Nope. Because the only thing causing it to accelerate is the Earth, so it cannot accelerate faster than that for this type of question. Then it could, based on, it could go up to whatever the acceleration on that planet is. Josh, I saw your hand.
If M2 happened to have a negative mass,
Doesn't.
but if it did, would M1 accelerate faster than?
If there was such a thing as a negative mass, yes. Nick Bernard.
Now, if I had a racquetball and a racket and I was fall, I jumped out of a plane, and then I took the ball and I went whoop-ah, and it went straight down. Couldn't that go faster than that?
Yes, that could accelerate faster
I was
than
gonna
that.
say,
Yep.
What's like the highest acceleration due to gravity?
Jupiter, I think, is 27.4 meters per second squared.
Oh.
That's
Is
fast.
that because it's
3
all
times
gaseous and it needs
that
to keep all the
exactly-
gas together?
It's because it's big.
I had a question, but I guess indirectly it was kind of sort of answered by Nick's question.
Perfect. Glad I could help. So we find the acceleration is 6 meters per second squared. The next one, determine the tension in the rope. In order to find the tension in the rope, we need to choose a system that has the rope as an outside force.
M1.
Cool. Evan wants to choose M1. Other people want to choose M2. Do it up. Does not matter which one you choose. You can choose M1. You can choose M2. I'm going to choose M1. So I'm going to say system is M1. If you want to choose system as M2, that's perfectly fine by me. So system is M1. So we're also going to use Newton's second law. A equals F net over M. For M1, we can write our net force equation as Fg1 minus Ft. And since our system is just M1, we're not going to use the combined mass. We're just going to use the mass of M1, which I got as 2. Oops, I'm sorry. I meant to write that in as M1 first. M1. We just found the acceleration in the last part, and we found that acceleration is 6 meters per second squared. Go through and find the tension of the rope. What did we get for the tension in the rope?
8 newtons.
We agree with Evan?
Yes.
8 newtons. If you got 8 newtons, that's what I got. You can high five your partner.
Oh.
Oh!
And you can turn the page to the next page. Next page. Different type of pulley question. Our approach, the exact same as the last pulley question that we did,
But we have friction now.
but a different type of pulley
Oh, no.
question. A blank kilogram hanging mass is attached to a blank kilogram mass M1 at rest on a magical frictionless table. The reason why I'm saying blank is because I'm going to mass this out and we're going to see how close we can get to the value of acceleration as we calculate it. These carts are 500 grams, and I'm putting an extra 1 kilogram on top. So we had a 1.5 kilogram cart, and our hanging mass is,
Yeah, I thought the cart was.
Yeah, it was 250 grams.
oh,
when we did
it's
that.
250?
When we did it on the last one.
Was it 250? Okay, so we'll say 250 grams, my fault. So 1.25 kilogram cart on A, and I'll mass this. With this on there, the hanging mass is, let's see. $34 grams.
We have to put that in kilograms.
Yes, sir. So we got the, we had the hanging masses, points, what did I say, 34 grams?
Yeah.
0.034 kilograms is attached to a
Yes.
1.25 kilogram mass 1, kgs, mass 1, at rest on a magical frictionless table. Draw accurate free body diagrams for each individual, it says pulley, my bad, each individual mass. You guys do that, and we'll do it together.
Is it the one that's moving?
Yep, we'll say that it is moving. Good question. Force of tension. And then for the hanging mass, we have a tiny force of gravity. Which way is this thing going to accelerate?
Right and down.
Right and down, so it's going to accelerate like that. I agree with that. So that means on mass 2, the force of gravity should be bigger than the force of tension. But the force of tension is equal on both because Newton's third law. For the next one, draw an FBD for the system of both masses. I'm going to do exactly what I did last time. And I'm going to take this and I'm going to stretch it out so it's just, there's our pulley. That was a horrible pulley. Please let me try again. There's our pulley. Man, that's so much better this time. So there's our pulley. And we'll say that mass M2 is attached on that side of the string. And mass M1 is on a table right there. And the reason why I'm doing this is to show that the force of tensions are internal to our system. So right there, for mass M1, we have the force of gravity from 1, the normal force also, force of tension to the right. And for our pivoted mass 2, we have the force of gravity from mass 2, causing it to accelerate, force of tension inside of our system. Those are equal, and since when we choose our system to be both blocks, those forces of tension are inside of our system. So the thing that's making this accelerate is the force of gravity from mass 2. So if we shrink these down to a point in the system like this, have the normal force here. Force of gravity from 1. Normal force, those are equal to each other. And the force of gravity from block 2, G2, being the thing causing it to accelerate. So that means our net force for the system of both masses is Fg2. Do we buy that?
Yeah.
I buy that. That makes sense. That's the unbalanced thing. That's the thing that's causing it to accelerate. Next step, predict the acceleration of, it says block M1, but aren't they just going to accelerate at the exact same rate?
Yeah.
Yeah, so predict the acceleration of the system. My hint to you is choose a system involving both blocks. As you guys are choosing your system and predicting the acceleration, I'll set this up so we can see how right or how wrong we are.
Do we use 10 or 9?
We'll use 10. It'll be close enough.
Is gravity still 10?
We'll still call gravity 10. And again, there's another self-check here because you know if you get a value for the acceleration over 9.8 meters per second squared or over 10, since that's what we're approximating it as, you done goofed. Since we're looking at the mass of the system, make sure that you use the mass of the car plus the mass of the hanging thing. I don't know what we should expect for an acceleration because I didn't know what the masses of those things were ahead of time. So when you think you have the acceleration, call it out. We'll see.
I got 0.264797508.
I also got.
Exactly?
I
Well,
rounded.
I rounded.
Good. So 0.26, 0.265, 0.27 meters per second squared. Cool.
Well, it would be.
It would be 2.26.
0.26 meters per second squared. Okay. I'll do a lap if anybody wants assistance. Okay.
Maybe a piece of parchment.
How about someone near you? Make sure we're okay. So we're going to go with a class prediction of 0.27 meters per second squared.
0.26, but yes.
All right. Evan is very concerned. 0.26 meters per second squared. Okay. Now we're going to test this the way we did it for the lab. We're up there. We're going to have a velocity versus time graph. We'll find the slope of it to give us the acceleration. Now, do we expect this to be exactly 0.26?
No.
Higher than 0.26?
Yes.
Yes, because friction is on this, even though it's very small.
That would make the acceleration
0.264797.
Okay, so we expect it to be a little higher than 0.26 because we meters per second squared because we rounded down.
But it's going to be slightly slower because there's friction as well.
And we use a different acceleration than the ground.
So we use a slightly different acceleration due to gravity. What outside factors other than rounding or math are there that we didn't include in our calculation?
Friction. Air.
Air, friction,
And
pulley mass. So when we do this, we say that this is a magical massless spring on a magical massless pulley. But we also know that that's not true at all. Just to kind of make sure that I have a little bit of room for this to accelerate, I'm just going to wrap this around the time.
Yeah, space.
Yeah. That's big.
Hear the friction. All right, let's test it. See if we were right or not. Evan, you want to be my catcher of stuff? Ready? Set. What do we predict?
0.26.
0.26.
Okay, ready? That's some good looking data right there. Let's see how right we are. Zoom in. Collect, fit, linear fit. 0.316 meters per second squared. And what did we predict?
0.26.
So it accelerated fast.
So it accelerated faster than we expected it to. Any additional thoughts for why? Or things that we neglected? Or things that might be happening here that we didn't take into account?
Why is it still
You wrapping the string around the cart do anything?
Me wrapping the string around the cart, I don't know if that would have made it go slower. I legitimately just wrapped the string around the cart so it would have more room for it to accelerate.
Wouldn't that increase tension or something? Maybe.
Did we mask it with a paper clip?
No.
Yeah.
Wonder if that changes it that much. What was it last time?
0.034.
34.
Oh.
With a paper clip, it's 35 grams. Did that change anything either? I literally don't know. I am wondering. I'm not like doing some weird teaching technique right now. I'm just trying to figure it out. So I don't know if that would change it because we're off by a good chunk.
Did you just change it to 2.7? 0.27.
It would have just changed it to 0.27 meters per second squared,
Yeah. 0.27 and a quarter.
which that doesn't account for that. What's one other thing that could be happening that I just thought of?
The cart isn't exact.
Maybe this could be slanted.
Well, that's what I was saying when I was up there. If you move that weight right now and the weight was already up here, it starts to roll down this way. That's
Right, so yeah, maybe this is actually slanted a little bit, which so I've noticed that if this was perfectly level and I let go, it would just sit there.
But it's not just sitting.
But it's not just sitting. Great observation, Josh. But it's not just sitting there, which leads me to believe that this is slanted. Since it's slanted forwards, we got a slightly higher acceleration. If it was slanted backwards, what do you think would have happened to our acceleration?
less.
Lower.
Slightly lower acceleration. Yeah, no.
So if our math and everything was completely correct, if you found the acceleration of it falling without the thing falling down and subtracted that from that acceleration, would it be?
You wouldn't have had to subtract it. There's something else you would have to do. We don't know the way to approach that yet, but you're right that you could have included that and we would have been right. Yes. So the outside force we didn't think about was the fact this thing is slanted. If you are good with that, that's a pretty good prediction. We were close enough for the things that we had. High five a human near you. Calculate that force of tension. Then we'll take a 2-minute break. To calculate the force of tension, you'll have to choose a system where the force of tension is an outside force. Where it says explain any differences, that's where you should explain some differences. And saying an answer of friction for explaining the differences, that doesn't really work because friction would have made it lower and it was higher. So if you said that the value is different because of friction, that doesn't really check out because friction would have given us a lower value than we expected and we got a higher value than we expected. If I was really dedicated, I would have come out here with a level earlier today and made sure that was perfectly flat. Not dedicated.
Is there such thing as a perfectly level surface?
Just like there's not such a thing as a perfectly frictionless surface, you can get really, really, really close. but there's always some imperfections in the atoms.
So we're using obviously our acceleration found on here, not the actual one, right?
Yes, yep. So for the force of tension, the block that we have to choose to find the force of tension is, well, I guess we could use either one. So if we use block 1, I'll use block 1. I'm just going to do it up here because there's no room down there. Oh, look at how there's room. Block 1. So we can do A equals F over M. And what do we get for a force of tension?
I'm still working.
0.26 meters per second squared for the acceleration. The force of tension is the net force
I got 0.325.
for block 1.
I have 0.23.
Kilograms. Let's see. So if I'm just using block 1, 0.26 times 1.25. I got 0.325 or 0.33
Yeah,
newtons, depending on how we round it.
Why is there just a force of tension?
So if we're just looking at block 1, here's our system, Nick. Right there. So the force of gravity and the normal force are in there, but they're balanced with each other up and down. So when we write our net force equation, net force is just the force of tension for block 1. So I got a value of 0.33 newtons. Ft equals 0.33 newtons. If you guys also got 0.33 newtons, seems like this is a good spot to take a 2-minute break before we try and do one of these on our own. 2-minute break starting now.
I thought it. I forgot.
That took 32 minutes and 45 seconds.